I'm gonna go and pin this. What can I help you with?
Yeah, I just want to ask a few questions about the test.
All right.
Yeah, you said you were going to cover like chapters on chapter four. Are you like more going to go into the beginning of chapter four or the end of chapter four?
Do the whole thing.
Oh, the whole thing. So it's like,
Yeah. So
oh,
test two, it starts with section 4.1, and in section 4.1, the whole chapter's on proofwriting, right?
proof.
But 4.1, what do we have? Even, odd,
Mm.
prime, composite, perfect square, and then 4.2, you're supposed to definitely read that because it's just a really great section that gives you information, about writing proofs. And then 4.3 was about rational numbers.
Rational numbers.
And then 4.4 was about the concept of divides
Oh yeah.
and standard factored form of an integer n greater than or equal to 2, right? And we had a mod D, and no, we didn't have those until 4.5. And that was 4.5. Yeah. 4.5 was A mod D and A div D and the QR theorem that says if A is an integer and D is a positive integer, then there exists unique Q and R in Z such that A equals DQ plus R, where the remainder is not too big and it's not negative. And then proof by cases. And then 4.7 was proof by contrapositive and proof by
Or,
contradiction. Go ahead.
yeah, you're saying proof by cases was 4.6?
4.5. We
Oh,
didn't
four
do
five.
we did yeah, we didn't cover 4.6.
Oh,
We didn't cover 4.6. And then 4.8 was more uh proof by contradiction, and what square root of 2 is irrational. I'm not going to ask you to prove the square root of 2 is irrational.
oh.
Those are the main ideas that we need to know. It's all about, you know, proving statements, and there's two different kinds of statements, and how we prove a statement it really depends upon whether it's a existential statement or a universal statement. And the main difference between these is existential statement, proof by example is okay. But for universal, we cannot use an example. We have to use variables and definitions and algebra and stuff, and things we may assume without proof. Do you have any particular questions?
No proof. Oh.
Things like the zero product property, that if x is not zero and y is not zero, then the product xy is not zero. And things like if sums of integers are integers and products of integers are integers. differences of integers or integers. We don't have to prove those. We can just use those facts, okay?
Yeah.
And then we learn to disprove statements by proving the negation. I mean, that's basically what disproving a statement is. It's proving its negation. Maybe you remember that. Disproving a statement, it amounts to proving the negation of the statement. So one way or another, you got to prove something.
Yeah, yeah, I understand.
So if you're going to disprove an existential statement, you have to prove its universal negation. If you have to disprove a universal statement, you prove its existential negation, and then you use these guidelines. Here, you have to verify X is in the correct domain, and then you go ahead and verify P of X, whatever the property is. So an existential statement looks like for all X in some domain. No, excuse me, existential. There exists an X in some domain D such that P of X. That's what an existential statement looks like, whereas universal statement can always be written as an if-then statement. We learned that in chapter 3. So for all X in D, if P of X, then Q of X. So one of the main things we learned how to do was that if we were given a universal statement, one of the first steps is to write it as an if-then, so we can get our eyes on the hypothesis and get our eyes on the conclusion that we wish to show. Okay.
Because, um, and for the homework, can I'm gonna drop it like in your um how do you call it? In your office tomorrow if doesn't disturb you.
I'm so sorry. I don't understand what your question is. Are you asking a question or just making a comment?
I'm asking a question. If tomorrow, if it's possible to drop uh homework 7 in your office tomorrow.
Yeah, sure.
Uh,
That's fine.
uh,
Drop it by 5 p.m.
oh, yeah. Thank you.
Uh-huh. And I think day 13 notes and day 14 notes should help you with that.
Day 13 and 14. Yeah.
13 and 14. Because 13 was proof by cases and 14 was proof by contrapositive.
Yeah.
Both those problems in homework 7, problem 3 and 4 on indirect proofs, those are both easiest proof by contrapositive.
Yeah, yeah.
But yeah, and in homework 8, you want to use proof by contradiction.
Contradiction, yes. Oh yeah. Yeah, but um homework 8 is not is like
It's going to be due next week at the beginning of the week. It's just 2 problems.
uh,
But both of those you should prove by contradiction because they involve one rational and one irrational, and any kind of statement that involves one rational and one irrational should be proven by contradiction for this class. Now,
yeah.
if it was a statement about 2 rational numbers, you can just prove it directly, probably. But if it's about a rational and an irrational, then the result probably says something is irrational, and you need to prove that by contradiction.
Okay. So the test, okay. All right. That was
So, yeah,
uh-huh.
so the test, might have some definitions. And then you're going to have maybe one of the standard factored form questions, either to give the standard factored form or where you had to find the smallest integer k that made a particular expression a perfect square. That was a homework problem. And there'll be a mod and some mod and div problems, or at least one mod and div type situation. And you'll see a proof by cases for sure. You're going to see a direct proof involving one of these, maybe a disproof involving one of these, and then there'll be a proof by contrapositive for sure. And then
And contradiction of
maybe a proof by contradiction, or maybe I'll just ask you to set up a proof by contradiction, but you should be able to prove something by contradiction for sure. Definitely, you're going to see contrapositive.
positive.
You need to be able to, do these. We spent all week on these this week on
Mhm.
on this, you know.
Mhm.
Are you Tuesday, Thursday, or are you Monday, Friday? Oh, Monday, Wednesday.
Yeah, Monday, Wednesday.
Okay, so you were there today?
Today, no, I wasn't there today,
That's too bad.
but I was there Monday and last Wednesday.
That's good.
So,
Yeah, it's tough when you miss class. This stuff, it's a lot easier to understand it if you come and hang out and listen to the discussion and practice, writing the notes. And today we workshopped after today we proved the square root of two is irrational. That's a beautiful little proof. Are you able to come to the lecture tomorrow, maybe?
tomorrow at what time?
I'll do it twice. I do it at 2 and I do it again at 3:30.
Yeah, I'll be there. Two,
All
three,
right. So it's in the room next door.
room next
You
door.
know how we meet in 128?
Yeah,
Uh,
wondering.
the, I'll be next door in 129 tomorrow at 2 and at 3:30. I give the lecture twice tomorrow. Same lecture. It's a nice, pretty little lecture. You'll enjoy it.
1 hour, right? Or 1 hour 30,
It's 75 minutes.
75.
Yeah,
Okay.
our class is 75 minutes, 2 to 3:15.
Yeah, yeah, yeah.
And then I do it again from 3:30 to 4:45.
Yeah.
Even if you could only stay for an hour, it's better than, if you come on time, you want to come on time
I'll
because
be there.
good stuff happens at the beginning.
Mm.
That's when we motivate, why are we trying to do this? Well, why do we care? Why do we need this kind of stuff? It's always good to get there on time.
Okay.
Yeah, it'd be great if you can come tomorrow. There'll be room for you. There's a lot of room in the 3:30 class.
Okay.
3:30 to 4:45, there's always a seat in there. But you can find room in the 2 o'clock class as well. Great.
Yeah.
And then we
Mhm.
spent after we proved the square root of two is irrational, we're going to spend the rest of the time just workshopping on doing the homework. We can either work on 7 or 8, whatever you need to, and I'll be circulating around answering questions and helping you out.
Oh, okay.
Yeah, it's going to be a nice class tomorrow because we're going to work on homework. Because it's kind of that last push to make sure people can write these proofs, before uh, we sit for the test next week.
Next week. It's next Wednesday, right? Yeah, next Wednesday.
Uh-huh.
Yeah.
Yeah, because I want to give you your homework back on Monday
Yeah.
or Tuesday, depending on what class you're in. You're in the Monday class, so I want to get that back to you so you can study it and maybe, rework some of that if you need to. We'll start some new material on Monday, but it won't be on the test. It'll be on the third test. We're going to start chapter 5 on Monday, but that won't be on the test this coming week. It'll be on the last test.
Yeah.
Good. I'm glad you popped
Yeah.
in. Can I answer any particular question? Is there anything in particular that you've struggled with?
Um, I mean, yeah, the one homework, one question. Okay.
Which homework was it? I've got 4, 5, and 6 sitting right in front of me, and 7 too. Which homework are you having trouble with? Hmm. I'm going to pause this while you figure out what you want me to want to ask. Okay, I'm just going to pause the recording. Apparently, I forgot to start the recording again. Um, Brandon asked about special homework 8, number 2. So I'm just going to talk through that now because the notes are here. This is a statement we're asked to prove in special homework 8, problem 2. For all x in the reals, if x is rational, then the number 3x minus 7 square root of 2 is irrational. So it's an if P then Q type statement. It's a universal, conditional. And the hint is we can assume square root of 2 is irrational. Well, all these proofs, these statements involving one rational and one irrational, in this case, the irrational square root of 2, it's going to be proof by contradiction. And what we're going to wind up contradicting is the irrationality of whatever the irrational number is. Here it's square root of 2. I think in problem 1, y is irrational, and we wind up contradicting that. But that's really the only thing we can do with the fact or hypothesis that the quantity is irrational. About the only way we can use such a statement is to contradict it. So we're going to contradict this. So the first part, A, was to please write the negation of this original universally quantified conditional. So of course, when we negate it, the for all switches to a there exists. And then, of course, to negate an if P then Q, we take P and not Q. Okay, so the negation of an if then is not another if then because it would be a universal and we can't have the negation of a universal be universal. It's an and statement. So we keep P. So there exists an x in the real such that x is rational and 3x minus 7 square root of 2 is not irrational. Well, that means it's rational. Okay, it's one or the other. If it's not irrational, certainly real, okay, then it is rational. So this is our negation. So in proof by contradiction, and you are prompted to use a proof by contradiction for this problem, just assume the entire negation, whatever that is, and here it is. So we're going to assume there exists an x in the reals such that x is rational and 3x minus 7 square root of 2 is rational. So you just assume the entire negation. Our wish is always the same for any proof by contradiction. We wish to show that this assumption leads to some kind of mathematical absurdity, also just called a contradiction. Then, of course, the definition of rational is in play twice, right? Because x is rational, and so is 3x minus 7 radical 2. So, you write your equation for x, like x is, I don't know, a over b, when you say all the requisite things about a and b. And 3x minus 7 radical 2 is rational. So we set it equal to, a quotient of integers. Just pick your letters, like c over d. And then again, because square root of 2 is irrational, we're going to try to contradict that. So we set the larger expression equal to itself, and then we make substitutions. So x, we know we've got some, x was rational, so we've got some kind of quotient of integers to plug in for x. And 3x minus 7 radical 2 is rational, so we've got something to plug in for this entire right side. Then you just do the algebra and get square root of 2 to stand alone, and it'll turn out to be rational, and that'll be your contradiction. Okay, so Andrew, you've joined us now. I'm talking to myself because I had paused the recording and the student asked this question about special homework number 8 problem.
Mm.
And so we talked all the way through it with him in the room. And
Oh
then
yeah,
he,
I didn't know if you were like recording something
yeah,
for
I am.
the
I'm
class or
record.
something.
Yeah, but so because I forgot to unpause the recording.
Yeah, no, that's
So I was just talking through how to prove this number two uh, and the bits and pieces, not all the details, but just enough. Enough.
yeah. Is that gonna be posted in the folder?
Yeah, I'm gonna post this here. So you're joining me here at sort of the 11th hour.
Yeah, I know.
It started at 8 and we're at 8:52. Do you have a quick question that you can
Yeah, it's
ask
just a small question about number two that we were working earlier in your office hours.
on homework 7 or homework 8?
Yes, on homework seven, that is correct.
Okay.
For my five cases,
Oh my gosh.
yeah, yeah,
Oh my gosh.
this was quite a bit of work. For the first one, I got n squared equals 5k, which was given. Yeah. Oh, you want to write this down? Okay, no worries. I can slow down.
Did we call it N or X?
For number two,
Yeah.
it's if n is in integers.
So if
So it's
N
n
is
in
in
z.
Z,
Yes.
then
N
either
squared
N
is
squared equals
5k,
5K or
or
N
n
squared
squared
equals
equals 5k plus
5K plus
1,
1
mhm,
or
or n squared equals
equals
5k plus
5K
4
plus 4. And
for
K
some integer
is
k.
some integer. So this is our compound conclusion.
Yes.
Right?
There's
Our
lots of them.
hypothesis is super simple. It's just that n is an integer. But our conclusion has, it's a big or statement. And if we can get this or that, then we've got Q of n, right?
Exactly.
So what was D?
D, I had for the divisor, I had five.
Yeah, D
Five
is
cases.
5 because see, we're dividing by 5 and either getting a remainder of 0, or we're dividing by 5 and getting a remainder of 1, or when we look at a perfect square and divide it by 5, we're getting a remainder of 4. I mean, it's kind of cool because n squared is a perfect square. It's saying if you divide a perfect square by 5, you'll never get the remainder 2 or 3. You'll always either get a 0, 1, or 4 for the remainder when you divide n squared by 5.
Yes.
So there are 5 cases. So was there any particular case that you had issues with, that we needed to look at the algebra for, or was it setting up the cases, or
No,
what's going on?
I think I had all the cases set up correctly. Um, I just wanted to make sure that in each specific case I got the right conclusion. As
Oh, okay.
you know,
All
n
right.
squared equals 5k or the plus one or plus four. I just wanted to
So
check and
if
make sure
n
that
equals
you know.
5q,
Mhm.
then n squared turns out to look like 5k. Yeah, because you can pull a 5 out of 25q squared, right?
Yeah, and I have k equal to 5q squared.
Yeah, that was right.
Yep. And
Case
then
2, n is 5q plus 1. What happened?
it turns
I think it's 5k plus 1.
yeah, it is 5k plus 1. Case 2 is 5k plus 1.
And k is
And
turns
k is
out to be
equal
what?
to 5q squared plus 2.
2q.
2q, yes.
Okay, good. That's right. All right, case 3 was n equals 5q plus 1. Of course, all this algebra, must show, the algebra. I'm not doing the algebra. We're just checking your work here.
Yeah,
Oh,
I have the algebra in here.
all right. So when it's 5q plus 2, what
Yeah,
remainder did
5q
you
plus 2
get?
for 3. 4.
Yeah.
So
And what was your k?
k is equal to 5q squared plus 4.
Nope. When you
It's not
square
plus.
this baby, you're going to get 5 times 2 is 10. You're going to get 20q when you pull 5 out of, oh, it's 4q. 4q.
Yeah.
See, you're
Oh,
forgetting your
4q.
q.
Yes. I missed the q. That's very
Yeah,
important.
don't forget your q in that
Let's
middle
put a
term, those
q
middle
there.
terms, right? What about case 4 when n is 5q plus 3? What'd you get? Oh,
Case
good for
4,
you.
case 4, I had let K equal 5Q squared plus 6Q plus 1. So it's N squared equals 5K plus 4.
Yes,
Or
because the
4K.
9 is 5 plus 4. That's
Yeah.
right. And
And
K
then
is equal
at the
to 5
bottom,
Q squared
I put
plus.
what we had in our work, which is by the QR theorem with divisors equal to 5. We know that, all those n squared products, n squared plus 0 plus 1, 2, 3, and 4.
Right.
Bottom.
This is the correct K for case 4. Don't forget your plus 1 because you pulled a 5 out of
Yep.
this 9.
That's
Great.
exactly what I have.
Oh, it's awesome. Your algebra, yeah, your kung fu is strong.
All right.
All
And for
right.
number 5, it
Uh-huh.
was K is equal to 5Q squared plus 8Q plus 3.
Let's see. Wait a second. 20, 40. Yeah, plus 8Q
Plus 3.
plus, that's right, because 4 squared turns out to be 16. So you pull out 3 fives from that. And so what's your
Yeah,
remainder?
15 plus 1, and then the remainder is plus 1.
That's right. You did them right.
And then for a conclusion sentence, I said for all cases we found that for every integer n, it falls into one of the given 5 cases above. Therefore, the statement is proved.
Um, the conclusion isn't that it falls into one of the 5 cases. The conclusion is that we get one of these 3 possible components of our or conclusion.
Okay.
So if n is an integer, then n squared either looks like this or that is our conclusion. The 5 cases come directly from the QR theorem. That's not our conclusion, but it gets us to the conclusion that we want, that the remainders are either 0, 1, or 4 in every case.
Yes. Yep. And
Okay.
then for number 3, I got one last thing for you, and that's the correct hypothesis for it.
Okay, number 3. What was the statement in number 3?
For all integers x, if 7x squared is even, then x is also even.
And I hope you proved this by contrapositive.
Yeah, so I'm actually on the third step of it right now, where the wish is. I just want to make sure that I have the correct hypothesis for this. I said that assume x is odd, and that's B.
Yeah, because the contrapositive is if X is
If x
odd.
is Yeah, I said if x is not even, then for all integers 7x squared would be odd. I don't really think that's like, the correct way to say it.
Usually we put the quantifier out front, but I'm not gonna dink you for that because honestly, in English, uh, we don't often always speak the way we write. But this is sort of the easy way. It's the contrapositive, so it's still for all. And then you got your not Q and your not P. Yeah, that's correct.
Beautiful.
Oh man, I'm proud of you.
Yeah, since that is the time you have, I will not keep you any longer.
Well,
You have a great weekend, and I will see you again on Monday evening or Monday.
Sunday night, Sunday night.
Oh yeah, there is Sunday night. Yeah.
Sunday from 7 to 8, and I'll try to get there on time on Sunday
Okay.
night. And if y'all need a pop-up, later in the week on, Monday afternoon, we have our in-person office hours like we did today. We had some time to do it today. We'll be in person in my office from 3:30 to 5 on Monday, okay?
And that's the big one because that's basically the
That's
one with
the
the
big one.
test. Yeah.
Yeah, that's the big one. And then we have another office hour on Tuesday in person from 5 to 6. But you got to use that little courtesy phone to get back in the office area if you want to come to the Tuesday office hour. And I sent around instructions on that. There's like a paper
Yeah,
directory with,
there's a paper for it.
yeah,
Yeah, I think you sent out an email as well for it.
I did a couple times because I'm worried that people can't get back there after hours.
Mhm.
Students seem to have an issue with that for some reason.
Yeah.
Hey, well, Andrew, I'm so glad that you popped in. That was a perfect way to
I
spend our
was
last 10 minutes,
I was
man.
like I apologize for it being like super late. I was just finishing up uh
Hey,
question too. So I just wanted to make sure that, everything was correct.
You did. You did it right. You did it absolutely right. Just show all that algebra, and it sounds like your algebra is strong.
Yeah.
Great. Well,
Awesome.
rock on.
Yeah, I definitely will.
All right. Good to see you. And I like the lighting in your room. Is that the lighting
Yeah.
in your room? Oh, that is so cool.
Yeah, it's just just to put up LED lights just to make it more spazzy, if you will.
I'm liking it. I'm liking that environment. You are ready to start streaming your vlog, man.
Yeah.
Okay. Well, I look forward to that.
All right, I'll let you go, Dr. Good. Thank you very much.
You're so welcome. Have a great night.
You too.
Good
Bye-bye.
night.